Hi everyone, in today's lesson we're going to take a look at parabolas. We'll be very familiar with parabolas from Pre-Calc 11. It was a major part of graphing quadratic functions. We're going to learn everything we did with that and a whole lot more, and we'll learn that parabolas are a type of conic and that there's actually a whole lot more to parabolas than what we learned in Pre-Calc 11. Some things will make it a little bit easier, and some things are going to make us think a little bit more in some new terms that we'll introduce in this section. So just to begin with, for review, the general form of a quadratic function, so this is back to Pre-Calc 11, took on the form of y equals ax squared plus bx plus c. And then we had something called graphing form, also called standard form, and that was in the form of y equals a x minus h squared plus k. And the point hk would tell us the coordinate, the x coordinate of our vertex. And the a value would tell us whether we have a parabola if it's positive that opens up or if it's negative that opens down. And then it would also tell us if we have some sort of vertical expansion or vertical compression. So I want you to now think about what would happen if you had a parabola that was, well, I'm going to say here, the Mr. Ricard sideways parabola. I don't know if you played rugby or you've seen Mr. Ricard on the sidelines at a rugby game, where in the past he used to celebrate with his patented sideways parabola. I don't know what to call it. It was his version of a dab, but it was a sideways parabola. So anyways, here we go. We have 4 graphs right here. All of them are going to be sideways parabolas, and we want to see if we can figure out what they would look like. So essentially what we're doing is we're taking the inverse of our y equals x squared parabola, and for our first graph we have x equals y squared. And if we have x equals y squared, what we're going to do is we're actually going to just turn everything onto its side. If we still have the point 0, 0, if we put input 0 for x, we get 0 for y. But what ends up happening is if I put in 1 for x, or I have something that produces a 1 for x, the y could have been positive 1 for positive 1 squared, or it could have been negative 1 for, and negative 1 squared would produce positive 1 for x. And so now if we used to have that idea of saying the amount you go over, you square to go up, it's almost going to take on a different shape. You would do the same thing, but almost on a different viewpoint. So now if we go over 4, we could go up 2 and down 2. And if you return back to 0, 0, the vertex, and you go over 9, you could go up 3 and down 3, and you create this parabola that would be on its side right here. And some of you may say that, well, this looks kind of familiar to some of the things that we learned with radicals, because if we wanted to isolate for y here, and you had x equals y squared, we could easily square root both sides, and then you could say y equals plus or minus the square root of x. And if you think about what we have graphed here, this top part here is y equals the square root of x. And if you reflect that over the x-axis, then you would get y equals negative the square root of x. And so it's just a parabola that's been turned on its side, or you can also look at it as a square root function with its negative reflected square root function on the same graph as well. So that's your basic inverted parabola. And based off of that, we can probably start to figure out what some of these other graphs may start to look like. Let's look at the second example right here. And it says x minus 3 equals y plus 2 squared. So think about what would happen if x has been replaced with x minus 3. That's a translation of 3 units to the right. And if y has been directly replaced with y plus 2, then that would be something that would be 2 units down. And if you wanted to put that all together, you could say, well, we were going to go 3 to the right, 2 down, and this would be our beginning point right here. And from there, you would have the exact same parabola as what you had in our first example. So we could go over 1, up 1, over 1, down 1, and then you could go back to your vertex. You could go over 4, 1, 2, 3, 4, up 2, down 2. And we can't fit too many other points on there, but we get the idea. And it could look something like that. Now, if you're trying to figure out how you can check to see what your graphs look like, you could go to Desmos and you go put that in exactly as is. You don't need to isolate for a variable or anything like that. But if you wanted to put into your graphing calculator, it's definitely a little bit more of a complicated process because you'd have to isolate for y. If you're feeling good about this and you think you could predict some sort of the expansions or compressions that are happening, feel free to pause the video now and try graph 3 and 4. Otherwise, let's see what we have here. So this right here, the y plus 1 means that we're moving 1 unit down. So we would have the point 0, negative 1. And it's a positive 2 that's in front of this. And the 2 is going to tell us that we need to do some sort of stretch. And if you think about what the 2 would mean in our traditional pre-calc 11 sense, that would be a vertical expansion by a factor of 2. This is actually telling us that we need to horizontally stretch it by a factor of 2. So if you went over 1, up 1, we're going to now have to go over 2 to compensate for that. So from your vertex, if I went over 2, I could now go up 1 unit. And if normally your next move would be to go over 4, we now have to go all the way over 8. And then we could go up 2. So everything is being pulled twice as much to the right as what it used to be. And if you imagine it being a mirror image of what you would have had for your regular parabolas in pre-calc 11, then hopefully that sounds familiar and that makes a little bit of sense. We'll put arrows on at the end there. And then finally, let's look at this last example here. So once again, this is going to tell us that we're going to go 2 units to the left, and we're going to go 3 units up. So if we go 2 left and 3 up, we're going to start right here. And now we have a negative, and this negative is going to tell us that our parabola won't be opening to the right, but we're actually going to open to the left. And the 1/2 is going to tell us that we're going to have to squish the amount that we were normally going over. So if you usually went over 1, up 1, we could only go over 1/2. And similarly, if normally you would go over, let's see, if you wanted to go over 4, 1, 2, 3, 4, then you would say normally I would have gone over 4 and up 2, but now we would have to change that, and you could say I could go over 2, up 2, and over 2, up 2, like that. And so you're going to get something that's going to be much wider than it was in the past. Okay, so again, kind of a bit of a interesting warm-up and something that might look a little bit different from what you were used to, but that's what sideways parabolas would look like. And we're going to build upon that concept coming up a little bit more. So definitely the complicated part of this lesson comes into some of the new terminology that we're going to introduce here. We're going to take a look at the idea of something called a directrix and something called the focus. So if we take a look at the more familiar regular parabola in the form of some form of y equals x squared, you'll notice that where you have your vertex, right above it, you're going to have a point, and we're going to call this point the focus. And if you notice right below it, you're going to have this horizontal line, and this line is going to be the equation of the directrix. And it just, by definition, the focus is going to tell us that if you take the distance from the focus to any point on the parabola, so here's the random point xy, and then you take that point xy and you drop it perpendicular down to the directrix, they're going to be equidistant from each other. They're going to be the same distance from each other by definition. And through that, we're going to be able to find out sort of a deeper understanding of what parabolas do and how they operate. So the exact same thing happens for our sideways parabola. So if you have your vertex, in this case it's right here, and this is in the form of x equals y squared, then if you go up, you create your focus, and if you go down, right there you have your equation of your directrix, and the distance from the vertex up to the focus is the same distance, this distance right here, as it would be to go from your vertex down to your directrix. That was the same in the first case as well. So given that, you can see what the definition is for a directrix and a focus. And if we read the point down here below, it's going to say when you have a vertex of 0, 0, you can actually now find the focus and directrix by being able to prove this. So this is a bit of an extension, and I would say it's something that's going to be a little bit challenging because we're going to look at some form of a proof. The key here to take away is that from here we're going to be able to come up with a formula to be able to apply the focus and directrix to other situations. So here's what we want to say. We know that by definition the distance of the focus to a random point P is going to be equivalent to that random point P perpendicular down to the equation of the directrix. And let's take a look at what we could do to label some of these points to be able to come up with something a little bit more general. So if we call the focus our first point, and we say this is x1, y1, and we call our point P, or second point, x2, y2, then using our distance formula, let's see what would happen if we filled in everything for our FP distance. We would have y2 minus y1, so you would have y subtract p squared plus x subtract 0 squared, all square rooted. And we would compare that with, on the right side here, our same P point that we can call x2, y2 as well. And right here, we'll say that this is our first point, and that's going to be x1, and y1. So then based off of that, if you wanted to input the values there and you had y2 minus y1, you would say it would be y subtract negative p squared plus x subtract x squared. And so from there, if you wanted to tidy that up and see what we could simplify, I would notice a couple things right off the bat. The first thing is let's try to square both sides. And if we square both sides, that eliminates the square roots from each other, and we can compare without the square roots, and we'd be left with y subtract p squared plus x squared, x subtract 0 squared. And then on the right side here, we would have y plus p squared, and then x minus x would reduce with each other, so it would just be y plus p squared. So let's FOIL out our y minus p squared, and we would end up with something that would say y squared minus 2py plus p squared plus x squared equals y squared plus 2py plus p squared. So from here, we can look to join some like terms, and you'll notice that parts of the left side and parts of the right side will reduce with each other. For instance, they each have a y squared, and they each have a p squared. And so if you wanted to start to simplify this a little bit more, if you added 2py onto the right side, you could now say that x squared is equal to 4 py. And another way of saying that is to say that you could rearrange the sides that they're written on, and you could say 4 py is equal to x squared. Both mean the exact same thing. All right. Okay, now you might be saying, what does all of this mean? What this means is we've created this strange 4p value that's going to go in front of our traditional y equals x squared, and that's actually going to help us find out the value of how much we need to travel up for our focus to find our focus point, and how much we need to travel down to get our directrix equation. And I bet a lot of you are probably going to want to ask some further questions in class on that. Now we could do a second proof here for what happens for the sideways parabola, and I'm going to speed it up a little bit and say if this is what we got for a parabola that opens up and down, then we're going to get something that would say 4px equals y squared for a parabola that opens on its side. Okay, so keep that in mind, and we'll see how we can apply that to some of our upcoming questions. Okay, so our first example here says, if you have a parabola with a vertex of 0, 0, and we pass through the point negative 4, 2, part A, can you find the equation so that it opens up? Okay, so that it opens up. Okay, so I want you to think about, we could even do a mini sketch if something like that help us out, but let's just see what we know from something like this. So think about the equation that we just created in the form that we had. We had something that said 4py equals x squared. And that's when it had a vertex of 0, 0, and it passes through the point negative 4, 2, where that's an x point and that's a y point. So we could substitute in 2 for y, and we could sub in negative 4 for x, and we could see what we get from that. So you would get 8p equals 16, and p will end up equaling 2. And so then if you go back to the general form of what we have it in, where it says 4py equals x squared, and we sub 2 in for p, we could say that 4 times 2 would give us 8, and 8y would equal x squared. And that might seem very, very awkward, and you'd say, why are we doing this? Because I know how to graph a parabola, and that just really doesn't seem like the same way that I would have graphed a parabola last year. And I would have to agree with you, but hopefully I can help make a connection coming up here. So I'm going to show you a second way to do this as well. Imagine you had something like y equals ax squared, where a could represent some sort of our vertical expansion or compression. We don't need to put in any sort of translations or shifts because our vertex is at 0, 0. And if you sub in, so we're going to do the exact same question here. We're going to sub in negative 4 and 2. Then you would find out that your a value is going to be 1/8. And you could say something like y equals 1/8 x squared. And guess what? That is equivalent to what we have on the right here. Kind of something that looks a little bit different, but we found the exact same solution. So what would happen if we were doing this and we wanted to have it open on its side? So if we want to open on its side, let's take our brand new equation that we've been working with our p-value, and let's say 4px equals y squared. And then let's sub in negative 4, 2 for x and y, and we could say 4p, our x is negative 4 and our y is going to be 2. And we would get negative 16p equals 4, so p would equal negative 1/4. So if p equals negative 1/4, and you go back to your original statement here, you would have 4 times negative 1/4 x equals y squared. The 4's can reduce with each other, and you would get something that could be negative x equals y squared. Okay, so the next thing to say is with these forms of having this equation with a p in it, you'll be given these equations for future assessments. So if you have a unit test coming up on this, then you'll be able to refer back to having the formula for this. Okay, now not all equations have a vertex of 0, 0, and so because of that, we do need to make some generalizations. And here's what would happen if you now had something in which the vertex was h k. We'd be able to now have something where we can write this in an expanded form. So if our vertical parabola took on the form of 4py equals x squared, then if we wanted to write this in an expanded form with a vertex of hk, we could say 4p, and then we're going to say this: our y is going to move left and right k units, and our x is going to move left and right h units. And then we could get something that would be applicable to something where we don't just have a vertex of 0, 0. Now, in terms of our focus, think about what the focus is. The focus is the coordinate of the vertex, and then you've been shifted up. And so if you have something like this, the x-coordinate of your vertex is the letter h. And then based off of that, you want to go you want to go up p units. And so what we're going to say, it's going to be k, which is the y value of the vertex, plus p units. And that would be the equation of our focus. Now, we know that the distance that you go up from your vertex to get to your focus is a mirrored distance from what you would have to go down to get to your directrix. And so if you think about what your directrix would be, your directrix would be, well, the line y equals k would be a horizontal line touching the vertex. But if you went up to get to your focus by adding p, you're going to have to subtract p units to go down to your directrix. The equation of the axis of symmetry, this is something that we'll be familiar with. It's going to be x equals h, the x value of the vertex. And we know that if our p-value is positive, then we would have something in which we would open up. And if our p-value is negative, we would have something in which we open down. So pretty heavy content to go over this idea of how the focus and how the directrix works. If we take a look at our horizontal parabola, let's just write out what we had when we had a vertex of 0, 0. We had 4px equals y squared. And now if we have something in which we add in the vertex hk, we would say we could have 4p x minus h equals y minus k squared. Our focus would now be this. Our focus, remember, this would now be shifting things left and right. And so you would be taking your h value and you have to add p to it, just like we added p in our other example over here. And based off of that, your y value would also stay consistent. It would just stay at k. So you would have h plus p, comma k. And your directrix would be the mirrored image of dropping p units to the opposite of where your focus had gone. So if you added p for your focus, you have to subtract p for your directrix. And so we would have something in which you would say x equals h. That would be a line that would go through, it would be tangent to your vertex, but then you have to subtract p units. And the axis of symmetry would now be y equals k. If p is greater than 0, then we open to the right, and if p is less than 0, then we open to the left. Okay, now, given all of this, I don't know if it's going to be like this all the time, but ask me in class, and I suspect that you'll get the equations for the focus, directrix, and the equation with P for vertical and for horizontal parabolas as needed on an assessment. We can discuss that more in class. So this isn't something that you're going to have to memorize along the way, and hopefully it's something that you've learned and you would be able to create as well. So the next question is saying this: find the equation of a parabola that opens left and has a vertex of 4, 5 and passes through 0, 7. Okay, so if we know that we have a parabola that opens up, we know the form of what we're looking at. We want something in the form of 4p y minus k equals x minus h squared. It has a vertex of 4, 5, so we can say that means that we would have y subtract 5, and we would have x subtract 4 squared. And it passes through the point 0, 7. So now what we need to do is we need to sub in 0, 7 for x and y, and we can find out what our p-value is. So given something like that, you could say 4p 7 subtract 5 equals 0 subtract 4 squared. 8p equals 16. And p equals 2. So if p equals 2, you could go and you could sub that in back to where p is, and you could come up with your general equation for something like this. So you could say, well, 4 times 2 would give you 8, and it would be 8 y subtract 5 equals x subtract 4 squared. And that would be the equation of this parabola. A good extension to a question like this would be saying, hey, what's the directrix and what's the focus? So it might be something that you want to play around with. And it'd be great if you had some graphing paper to be able to help sketch that out a little bit as well. Okay, so our next idea goes back to something in which you'll remember a lot from Pre-Calc 11. We talked about it a little bit if you've learned circles already, and that's the concept of completing the square. So I'll just do a quick recap of how we complete the square. Its purpose is to be able to reshape what we have so that you can create perfect square trinomial terms that will allow us to talk about it in terms of more of a graphing form rather than a general form. So the process that we said here is from last year is this. If you have a leading coefficient, you factor out the leading coefficient as your first step. And then you'd be left with x squared plus 6x because you factored out the 2. You leave 2 blanks, and then on the outside of the brackets you have plus 4. And you want to invite 2 numbers inside the brackets. And to create a perfect square trinomial, you take the middle value, the b value, in this case 6, and you're going to, the coefficient of it, and you're going to take half of that value and square it. So half of 6 is 3, and 3 squared is 9. So you are inviting in plus 9 and minus 9. You always invite the positive number first, and then its exact same negative number. And the negative number needs to get kicked out. And remember that when you kick out the negative 9, you had previously factored out a 2. So its value on the outside isn't just negative 9, it would be negative 9 times 2 because that 2 needs to expand with the negative 9, and you would have a negative 18 in this case on the outside. So from here you would get y equals 2. X squared plus 6x plus 9 is an example of a perfect square trinomial of x plus 3 squared minus 14. And that would be how you complete the square. if you want, you can ask me in class about the a party analogy that we have, where the brackets is representing a house, and we're inviting people in, and they're getting kicked out. And we can talk about that if you think that would help with your sort of process of working through the algebra. Example number 3. Okay, so find the vertex, the focus, the directrix, and the axis of symmetry of something like this. So there's a lot at stake. Now, in order to begin this question, I would say right now it's in general form, and we need to put this in a some form of a graphing form. And so because we have something where we would need to create these brackets and put it into a graphing form, we need to complete the square. Take a look at what you have, and we know that this x squared minus 6x could be something that we'll be able to join together. So here's what I would recommend. We could say bracket x squared minus 6x blank blank, and then let's just leave the 12y minus 15 on the outside. And we're going to invite plus 9 and minus 9. And the back number gets kicked out. There is only a 1 in front, so when it gets kicked out, it remains a negative 9. And I'll just cross it off there to show that we did kick it out. And then you would have x squared minus 6x plus 9. And that would create a trinomial of x minus 3 squared plus 12y. And if I join negative 9 and negative 15, I would get negative 24. So from here, we want to put this in to our better form. And just to recall what that better form would look like, is it would be the form of 4p y minus k equals x minus h squared. And for something like this, I would recommend let's subtract the x minus 3 squared onto the other side. So if we did that, we could say we have 12y minus 24 equals negative x minus 3 squared. And probably we want to leave this negative. We want to get rid of that. So let's actually divide everything by a negative 1 as well. And if we do that, we could say now we have negative 12y plus 24 equals x minus 3 squared. And we're almost done. If I go up over here, the negative 12y plus 24, we want to factor out something so that we have it in a cleaner form, like this y minus k form right here. So let's factor out a negative 12. And if we factor out a negative 12, then we'd be left with y subtract 2 equals x minus 3 squared. I'm going to put a box around this, and this is the equation of what we're looking for. So a really good task for you right now would be to say, hey, are you able to find out the remaining components of what we want right here? So can you say what would be the vertex, and what would be the focus, and what would be the equation of the directrix, and what would be the equation of the axis of symmetry? So I would recommend pausing the video and seeing if you could come up with that right now. So to look at our vertex is saying, well, we've gone 3 to the right and we've gone 2 up. So we would have a vertex of 3, 2. We know the one that I'm probably best at next is to answer the axis of symmetry, and we know that this is a parabola that would be opening up or down because it's in the form of y equals x squared. And so the x value of the vertex is 3, which means that I would have an axis of symmetry of x equals 3. And then to find the focus, we know that the focus would take on the form of, let's see here. So the focus would take on the form of h comma k plus p. And so if we want to think about what that would produce a point 3 comma, and then our y value of the vertex is 2, and we're going to go up p units, and our p value here would be -3, because this was a 4, so I would need to times the 4 by -3 to be able to fully get there. And so because of something like that, we could say it would be, the focus would be at, let me think of this, we said that the y value was at 2, and then I'm going to go up p units, and so if p is -3, then it would be 3 comma 2 minus 3, and then that would give me the point 3 comma -1 for my focus right here. And then finally, for the directrix, we know that the directrix takes on the form y equals k minus p. And so if you think of your k value as being 2, we could say this would be y equals 2 subtract -3. And that would be like saying 2 subtract -3. So you could say your directrix will be the equation y equals 5. Okay, so definitely a whole lot of new stuff, probably a lot of looking back at your notes, but I hope that those parts make sense there. Okay, so here's our culminating example. If we have something here where they're saying now, find the equation of two parabolas that both have a vertex of 2, 4, pass through 0, 0, graph the relations, and label the vertex, focus, directrix, and axis of symmetry. So you should take some time right now and see if this is something that you'd be able to do. Assume that you would be provided with these formulas, and see how you'd be able to go from there. I recommend probably trying to, once you've got your equation, identifying what your p-value is, because once you have your p-value, then that'll really help with your focus and your directrix. And so just to get you started, if we have our parabola that opens up or down, just remember this is going to be the equation of 4p y minus k equals x minus h squared. And conversely, here you have 4p x minus h equals y minus k squared. Okay, so those are your options on what you're working with, and let's see how you do with it. Okay, so if you have a vertex of 2, 4, and that's a vertex of 2, 4 in both situations. Let's put this in here. So you could say 4p, and then we're going to say we have y subtract 4 equals x subtract 2 squared. And now we know it passes through the point 0, 0. So we can sub in 0, 0 for x and y. And if we do that, we would get, let's see, we would get -16p equals 4. So our p-value will end up being -1/4. So we have our p-value isolated right here. And based off of that, we're going to want to know what our vertex is, what our focus is, what our equation of our directrix is, and what our equation of our axis of symmetry is going to be. And if you're having a hard time sort of just looking at the formula and plugging it in, I would recommend maybe giving this a chance to be able to try to plot it. So a vertex of 2, 4. If you have something like that, we could go 2, 4 right here. Okay, and you can start to think about, well, what would this start to look like? If my p-value is -1/4, then maybe I could write my overall equation. If I sub this in here and I do 4 times -1/4, then I would just get negative bracket y minus 4 equals x minus 2, I'm running out of space, squared. And that's going to tell us that we have a parabola that is going to open down. Now think about what would be happening with the p-value from something like that. Well, the p-value is only a quarter, and so what that means is this: your focus. Actually, let's label some of these in, and then I think that'll help us out. Our vertex is going to be 2, 4. And our focus, remember, it's going to be the point 2, and then it's going to be 4, the y value of the vertex, and then you add your p, and your p in this case is negative a quarter. So it would be 4 plus negative a quarter, which is just going to be the same as saying, I don't know if you want to say 3 3/4 or what, 3.75, but it's going to be just less than that. So we'll say 3.75, and that's fine. And so that's going to be right here. And then you can mirror that with your directrix. So if you dropped a quarter to get your focus, you can go up a quarter right here to be able to get the line for your directrix. And your directrix is just going to be the line y equals 4 plus a quarter, or 4 subtract negative a quarter, so 4.25. And this is probably going to be a pretty rough sketch. But right there at y equals 4.25, I could have done that as a solid line. That right there is our directrix. We know that our axis of symmetry is the x value of the vertex, so x equals 2. And we have a parabola that's going to open down, and it goes through the point 0, 0, and you could mirror that over here. You could get something that looks like that. Okay, for your, hopefully you have enough room, but for your second, there we go, let's try this here. For your second equation here, okay, so once again, let's sub in the vertex right away. So you could say 4p, and then we would say x subtract 2 equals y subtract 4 squared. You can sub in the point 0, 0. And when you do that, you get 4p, 0 subtract 2 equals 0 subtract 4. You could get negative 8p is equal to 16. So your p value will be equal to negative 2. So if you want your overall equation for this, and you put negative 2 in for your p value, you would get negative 8 x subtract 2 equals y subtract 4 squared. And let's start to plot that. Our vertex was at 2, 4. And we have a sideways parabola. Whoops, 2, 4. We want to find our focus, our directrix, our axis of symmetry. Okay, so after the vertex, I always think the axis of symmetry is the next easiest one. So this one here is going to be y equals 4. And let's put that in right away. Okay, and then to find the focus, we know that our focus in this case, if our p value is at negative 2, then our focus would keep the exact same y value, and we would have 2 plus negative 2. So you would have something in which you have a focus of 0, 4. And that would be right here. And then, probably didn't label our focus very well for this point here. And then if you mirror that, and we've gone 2 to the left, then we know that we could balance that out by dropping down to here. And so if this is a line right here, this would be x equals 4. And that would be our equation for our directrix. And then we know we pass through the point 0, 0. And if you mirror that, you would have a point 0, 8. And that's enough information to be able to graph this sideways parabola. I probably should label right here, the focus here was at 0, 4, just like here, the focus here was at 2, 3.75. Okay, pretty heavy lesson. I know you'll probably have a bunch of questions for me. So right here, we have some questions to be able to start to look at. Let's edit this slightly. So let's say it's numbers 1 to 3 odds. Okay, and then we can take a look at 4 to 8, and most of those are just single word problems for that, so it's not as much as it looks. Okay, that's parabolas, the conics edition of that.